In this presentation, we're going to look at the variance test, which is the F test. So a chemical manufacturer using two production lines has made slight adjustments to the second production line, okay, in an attempt to reduce the variability, which is the variance essentially, in the levels of impurities in the chemical produced on that production line, okay. So 12 randomly sampled batches of chemicals were taken from each process. So we have this 12 here and this 12 here, okay. And the impurities are, the level of impurities are found to be as follows. So essentially what we have here is we have 12 measurements for process 1, 12 for process 2, and what we have here is the standard deviation of both, okay. Now you'll notice that the standard deviation of the second one is noticeably different from the first, but is significantly different, considering we're only dealing with samples of 12 in both cases. Using an appropriate statistical test, investigate whether the manufacturer has been successful in reducing the process variability for the process. That is to say, has the second process much reduced variability, okay? That's just to think about that, this value here being reduced down, okay? Explain your conclusions and stating any assumptions that you might make. So since 12 randomly selected batches were used for each of the two processes, we have independent estimates of the variances sigma 1 squared and sigma 2 squared. Now just remember, we're going to use the sample variances, which are derived from sample standard deviations. We just have to square those values. Now the null hypothesis is essentially that they're equal to each other, or you could actually formally more stated as less than or equal to versus greater than, okay. Now here, seeing it's a reduction, that means sigma 1 squared is greater than sigma 2 squared, okay. So the sigma 1 being the big one, sigma 2 being the small one. Just think about it for a second, it makes sense, okay. Now this is essentially a statement of no decrease, okay. And that's how we might write it mathematically. Just remember that the less than or equal to the less than or equal to sigma squared is a bit overkill, but it just like essentially does accurately say no decrease. So this is our variance terms here, okay, and essentially just square of what we have up there, okay. Now assuming that the distributions of impurity levels are normal, okay, the sigma 1 squared equals sigma 2 squared is distributed as an F random variable, okay. Essentially what we're getting at here is the variance ratio. Variance, I'll just write that in there, ratio. Now what you would usually do here when you're calculating this test statistic is sort of have it such that it comes as a value greater than 1, okay. So just adjust things in a way that it should, the test statistic value should come out greater than equal to 1, okay. Now but that has implications on our degrees of freedom, okay. So the whatever goes above the line would be reflected in the first case here, okay. So this S1 squared will be the first of our degrees of freedom, and the second one, which is the denominator, that will be reflected in the second of the degrees of freedom. And so essentially what we do is get, let's do that in black, we would do n minus 1 for both. Now it's not particularly important in this case, okay, because they both have the same sample size, but just in case you are, they have different sample sizes, this one belongs to the denominator, so the numerator, and this one belongs to the denominator, and it's n minus 1 of the sample sizes in both cases, okay. Just an important thing to consider. You don't have to do it like that, but I actually just favor just have one way of doing it, and that's it, okay. So make sure it comes out greater than 1, and the first degree of freedom corresponds to whatever the numerator says, and the second degree of freedom corresponds to the denominator, and in both cases it's the sample size n minus 1. Okay. Because if you get it wrong, you could get a totally different test statistic, critical value. So essentially, what we're going to do here now is get the critical value that corresponds to F1111, and it is 2.817. Okay, so sorry, just tracking back for a second here. When we do work out our test statistic, it turns out to be 3.49, okay, which is 0.012536 divided by 0.003590. Okay. Now, at a 5% level, okay, that's just that's important, and it's also it's a one-sided procedure. So it's a one-sided hypothesis test with 5% significance level. So the critical value is 2.817. So in this case, there is evidence of a reduction. Okay, essentially the test statistic is greater than the critical value. Okay, which means we reject the null hypothesis, and that means that there is evidence of a reduction in the process variability thanks to this new process. So that's it there. Now, essentially, just to sum up, the key thing there really is getting the variance ratio right and sort of getting the corresponding degrees of freedom for the critical value right. Okay, we'll leave it there.